In this video, we extend the functionality of the Tensor class. We add more essential foundational operations. These operations are necessary for building neural networks. I provide the reasoning behind each of the operation, and we will implement both directions, forward and backward passes. And I wanted to start from the squeeze method that removes dimensions of size 1 from a specified axis. And its backward function ensures that the gradients are expanded back to their original shape. If we manipulate with the shape of the tensor all the time, we need to transform this shape back during the back propagation. Let's define function squeeze, and we have self as the first argument. Axis, we can define axis as the union of the integer and tuple of integer, because we can drop one dimension or bunch of dimensions. And this is the optional argument, and by default it equals none. So, and we return back the tensor data type. So, okay, now we need to build an output. We will call the numpy.squeeze. Use self.data because we change our data, and axis equals axis. So the output is our output data in forward mode. So now we need to define dependencies list, and if self dot requires gradient, we need to define the backward function. We have the gradient, and just to make it shorter, we can copy and paste it right over here. We have the same type signature for the backward all the time. So if the axis is none, we remove all the dimensions of size 1 from the data. And it means that we need to reshape back to the original shape. If axis is none, we can return the gradient dot reshape self dot shape. Self.shape gives us the original shape, and we reshape the gradient back to the original shape because we need to be sure that the gradient dimensionality is correct in backward mode. So, and if we have axis that defined in the argument of the squeeze, we need to return numpy expand dimensions, and we put gradient as the first argument and axis as the second. So if we have the defined axis, we just expand the dimensionality of the gradient back based on this axis argument. So then we add to the dependencies list, append new leaf. As the value we use self, and as the gradient function we use this backward method. Last step, we can copy it from the exponential exp method. It will be absolutely the same. We return back new tensor with the output self requires gradient and dependencies list. Next, the unsqueeze method that adds a singleton dimension at the specified axis. It's some sort of the opposite action of the squeeze. Let's copy this method put it right over here. We have self as the first argument and the dimensions as the second argument. And we return back the tensor, of course. So we need to install the dimension argument. It's absolutely necessary, yeah? And it's unsqueeze, not just squeeze. As the output, we can use numpy expand dimensions and use self.data and access as the dimension. We follow the same API as in the torch. So then we need to create the dependencies list, and if self requires gradient, yeah, I can copy all this stuff right over here. And we need to return in the backward mode the numpy squeeze. We squeeze our gradient at the specified axis. In our case, it's dimension parameter from the argument of unsqueeze. So, and we need to append to the dependencies the same self value and gradient function as the backward, and return the tensor, yeah, at the end of our method. The view method allows a tensor to be reshaped without copying the underlying data. Let's define this method, view. We have self as the first argument, then we have shape as the tuple of integer. Yeah, we can have more than one, of course, and we just return the tensor back. So let's use the as the output self.data.reshape. With the reshape, numpy trying to do the best attempt to return the view of the data if it's possible. Okay, and we need to have dependencies, of course, and then if self requires gradient, we need to create the backward function, and inside the backward we return back the gradient dot reshape back to the original shape. Again, any manipulation with the data shape in backward mode, we need to change it back. We need to roll back any changes in the shape of the gradient, yeah, in backward mode to proceed our computations. So then we need to append to the dependencies list, I hope, the same value self and gradient function as the backward, and we will return the tensor, new tensor object with the output self requires gradient and dependencies. Let's test the squeeze, unsqueeze, and view. I just copy this tensor A, and let's create a tensor B, and we run, let's say, the view with the shape 1 times 4, and let's run b dot backward just to run the computational graph in the backward mode. And here we run numpy, let's say once like b.data. Let's run this code, and of course we need to initialize tensor and then run it again. Okay, it works. We can check the, let's say, a.gradient. Because we have the gradient graph, we run the computations in backward mode, and it means that for every node that requires gradient, we compute the gradient. And you can see it works fine. So we can add more operations. Let's say that we run the unsqueeze at the dimension 1. Okay, looks nice. Then squeeze at the dimension 1. We can run even more unsqueeze and squeeze. Let's add unsqueeze 0, and it still works fine. We can check the B gradient, yeah, and you can see it's quite different gradient shape. because for the b we started from this point where we transform the a shape to the vector, yeah, and we add 2 dimensions and squeeze 1. So, and in backward mode we just reshape everything back to the original tensor shape. Next is the clip method that allows us to restrict the values of a tensor to a specific range. It will be useful when we're gonna to develop the stochastic gradient descent optimizer. We will clip the values of the gradient. Let's define clip self as the first argument. Then we have the mean value, and we specified this mean value as the float, but optional float. By default, let's install none. And max value, the same data type and the same default value. Okay, and we will return the tensor back. As the first step, let's create an output, and we need to call the numpy clip self.data to the mean value and max value. Then we need to initialize the dependencies list, and we need to check if our tensor requires gradient. We then create the backward method, backward function. Okay, let's think for a moment what we need to do inside the backward step. The gradient is passed through the values within the range between mean and max values. It means that for the values that outside this range, the gradient is 0 because the operation is not differentiable. Yeah, we have no any changes in the values outside of this range. So our purpose is to create a mask, and we can create mask as the numpy once like the self dot data. And if the mean value is not none, if we specified the mean value, we need to set up for the mask self dot data less or equal than the mean value. For the values that is outside of this range, we install 0. It means that these values shouldn't commit anything to the gradient graph. And if the max value is not none, we need to do the same, but with the different condition: more or equals than the max value. We need to drop the values that more or equal to the max value, and we return the gradient multiplied by the mask. So when we multiply any value by 0, we just drop this value. We just zero out the values that is outside of this range. Yeah, we clip these values. We drop them from the gradient. That's our backward mode. So, and we need to add to the dependencies. We need to append leaf and value equals to self, and the gradient function is underscore backward, and we return new tensor with the output values, self requires gradient, and dependencies for the backward mode. We can test this method. Let's reinit our tensor, and we can run the a dot clip and define mean value, let's say 2, and max value, let's say 3. Run this code and you can see the result. We clip one and replace 1 to value 2 because the minimum value is 2, and 4 to 3 because the minimum value is maximum value is 3. Let's define the tensor b and run b dot backward numpy once like the b dot data. Okay, I hope that it works fine, and let's check the a gradient, and you can see the result. And I think that we installed 2 like high minimum value and 2 low maximum value. Let's use 1 and 4. In this case we cancel out only 1 and 4, because they less or equal to min value or more or equal to the max value, and it looks much better. We just leave only 2 and 3, only this counter diagonal elements for the gradient of the matrix A.